So last week we discussed about sequence learning problems, right? Um, so we discussed like RNNs, GRUs, and how we process like text data in using neural networks. And so yeah, the some of the tasks which we discussed were like the translation, captioning kind of things, right? So what do we do in translation? So all these tasks usually involve like a um, encoder and decoder architectures. That is, you encode the input statement and get a representation of your whole text, and then yeah, so you have a summary of what the input means, and you use that vector and pass it through a decoder to get your output. Um like in machine translation, where like in this example the translation is from English to Hindi, right? So through encoder we encode like each of these tokens and pass the whole uh, the summarized vector which comes out of at the end of the encoder here to the decoder, where step by step you decode one token after the other, like in this manner. Similarly, even in image captioning tasks, the instead of the input like sequence of words, we have an image, right? So that forms the encoder. So you can use a image encoder, like which could be a CNN. So I encode this to get a feature vector, which is a summary of the image. So given that summary of the image, which is encoded in the feature vector, pass it through the decoder to get an output, which will give out the caption. So the underlying architecture, one of all these models are the encoder-decoder architecture. So these are actually really old, as in. So they were originally proposed to learn image representations, right? So um, it so what where are I mean can you guys name any examples where this kind of architecture is used? I mean, other than the sequence learning tasks, just using images and an autoencoder. Image compression, yeah. So this code, will it be possible to explain a concept to demonstration? Uh, yeah, usually we do have some code walkthroughs, but I think for this week we don't have any code notebooks. Next week I'll make sure to find some. Yes. So yeah, right, image compression. So why, how can it be used for image compression? Why?
Because we are converting it into a lower dimensional representation.
Yeah. So it does dimensionality reduction, right? From an image space, we are getting a compressed vector here. So that actually which captures all the details present in the image, and just from that code we try to decode. So that is how we learn a decoder, right? So usually we can get rid of the decoder and then use just the encoder to get the lower dimensional representation of the image. Yeah, image compression, dimensionality reduction. Any other tasks? So if we give, while training an autoencoder, we give an image and we try to predict the exact same image. Like we give a clean image and try to predict the clean image. So you can unmute yourself and ask also. Fully connected layer of CNN fed as input to RNN. Yeah, this is used like in captioning, sentence completion. Yeah, definitely all these tasks it is used. In chances of data, I didn't really get your question. Can you can unmute yourself and ask. In while training autoencoder, you usually train it to predict the exact same image. Like I give a clean image, the target is to predict X. So the loss function usually is the mean square error loss. So I have my this is my ground truth input, and then this is the predicted image, and I just try to minimize this loss and learn the whole network so that it learns the image representations. So there are also these networks called as denoising autoencoders. Where you give the input is a noisy image. You pass it through the encoder, then the decoder, and you get an X prediction. And but you also have a ground truth. Like suppose you have clean images, clean and their noisy version, say Gaussian corrupted images or something like that, and you want to denoise the images. So in such case also you can learn an autoencoder where the objective is between the predicted the ground truth and the predicted image, but the input is the noisy image. So the model is the autoencoder is learning to denoise the image, right? So if you train it in this way, then the embeddings which you are learning will be more robust to any corruptions and as such. So they are usually better represented. So in such cases, these augmentations could be done. Augmentations in the sense, not where there is not like cropping and as such, but augmentations where you are like doing some color distortions or adding noise. Such augmentations could be given as input, and you want to recover the clean image. So these learn better, more robust representations of the images. So anyway, yeah. So all these tasks also do encoder decoder kind of mechanisms, but these are not exactly as the image autoencoders. So here in image autoencoders, it's usually a symmetric architecture, and yeah, you have like convolution, deconvolution layers kind of thing. But in translation tasks and captioning, sentence completion, all such tasks, so the encoder could be of one form, decoder could be of some other form. Like if you use an image, then the encoder will be a CNN, right? But if I'm using doing a machine translation task, then the encoder could be like an RNN, and decoder could be something else, but whatever is relevant to the task. But then so in this mechanism where I use an RNN to encode my text and decode, like what are the challenges that are involved? We did discuss this last week also, I think. Long range dependencies are hard to maintain, yes. So if I give like a really long text with some 5 6 sentences and I ask it to translate in the decoder, then it might not be able to encode or remember the information from the start, like the early statements, right? Vanishing or exploding gradients. Yeah, that is definitely while training time, yes. And also there are like other some other realistic this is so how we make statements in different languages differ, right? Like in the order in which we express things like nouns, verbs, and also on. But in a different language, so the standard way of expressing can be very different. Like in if this was the statement, the word reach is in the start of this, but the German translation of it, the word reach comes at the end. So in such a case, preserving the like the meaning and mm, meaning and like the order of it, so that it can decode it correctly for the new language is also difficult because of these long range dependencies. So all this happens because I am starting from the first word, so I encode that and then like I take in new information here. So this so at a particular place, if I interject here and then see whatever my so it's usually my hidden state, right? The hidden state at that particular time step or after those many tokens, it it has a summary of all the text until that point, right? So the hidden vector which I get out of this after encoding the statement comprises the meaning of the whole thing. That's the assumption. But then I also want to access information that comes early on, right? So that is usually addressed by this attention mechanisms where my the summary vector which I get right at the end, it is not obtained in the sequential manner. It's not just obtained as the final sequence. It also is a combination of all the tokens it has seen until that point, so it so that it doesn't forget stuff. So using an attention mechanism, if these were the input text and the hidden states, this is how an RN1 network would progress and we get the hidden states, right? So instead of just using this as my summary vector, the context vector, it would use that as well as so it would use that as the input to the decoder, and along with that also use mm, the another context vector CT, which is a combination of all the hidden vectors across time, and these alphas are the weights which we give for each token, like alpha t1 at yeah. So when I pass this in the decoding step, so this is my like summary vector here I get. So along with that I give another vector c1, which this c1 is a combination of all the hidden vectors here. So ci is like summation of c, okay, c at time step t to decode the tth word, right? Alpha t, and say there are whatever capital T tokens here, phi and hi. So I goes from 1 to t. So we decode it and then we have the next hidden state vector, which is a combination of my whole context earlier and the decoded token, right here, whatever I got here, that, and then it takes in the input context from all the tokens as well. So this is the decoding mechanism. So the modified part is adding these additional conditions here, c1 c2 ct and so on. And the scores, so Sure. Yeah. So to compute how much I want to each of these input tokens contribute to the current time step, I will take the previous hidden state, that is st minus 1, which I'm getting in the decoder. So I compare how similar. So suppose I want to calculate C2 here, right? I'll compute how similar C2 is with respect to H1. Like I mean S1 is similar to, so S1, like similarity score of S1 with H1, S1 with H2, S1 with H3, and so on. So this is the cosine similarity scores. So then I have obtained all these similarity scores, and to compute to convert, so all these, each of these will lie in the range 0 to 1, right, because they are cosine similarity scores. But because I want these alphas to be weights that sum up to 1, that is, if I sum alpha t across all j, where j goes from 1 to capital T, I want it to sum up to 1, right? Because say for one word I give higher probability, another one lower, and something like that. So to make this sum up to 1, we use the softmax function. So this is exactly like this function here is the same what we discussed in classification tasks, right, where we have the logits. So these things act like logits, and then you pass it to the softmax function to get the scores, to get the scores which sum to 1. Any questions in on this architecture? Like this was, I think, some 2017, not 17, 15 paper, I think, on where they proposed this for neural machine translation task. So this was when this attention mechanism was originated. So this part, right, of uh, combining, like at each time step I take a combination of all my input sequence words and use that to condition while decoding. So this is the like core of the attention mechanism. Is this clear, or like if anyone has any doubts you can ask me now. So yeah, so this task what we discussed here was temporal data, like what language task, right? Sequential task, like in NLP, what do we do, or in speech, these kind of things, where we have a sequence of words. So can the same logic be used in spatial data? That is, in the case of images. So how can this logic be applied in images? Let's see that. So in images, what do we do? In, to encode the images, we would usually use a CNN, right? CNN, and that is usually followed by a fully connected network that does some classification or something. But once we pass anything through a fully connected network, do we preserve the spatial information or not? No, right? Because like so as long as my feature maps are like this, um, two-dimensional, I still know that okay, like if I pick a feature from this corner, it will correspond to some region which comes in the corner of the original image. But then once I give this feature map through a fully connected network, then I combined all the information, then I only have global information, like a summary of the image. But there is no like there's no signature of what contributes to what. Like if I pick the first neuron, I mean the first output vector from the fully connected network, like I don't know what that value corresponds to in the image, like which area summary it is. I don't really know. So uh, so if you still want to preserve that spatial information or extract something out of it, what do? We ignore the fully connected layer, and right after the convolutional layers, so it would still be a 2D feature map, right, like this. So m cross n would be the feature dimension spatially, and then c is the channel dimension here. Yeah, so based on where I pick the feature, it corresponds to some region in my image. So so each vector here still has some special information. So if I want to do so I can treat each of these vectors here, like in my spatial feature map, as one like as one word embedding, which captures different regions of the image. So if I have an image like this, like it, although it's not exactly this because the receptive fields will overlap, so I can think of this as my first word, this as my second, third, fourth, fifth, sixth, seventh, eighth, ninth. As think of, if it is a 3 cross 3 feature map, then I can think of them as 9 words, like equal 9 visual words. So you can unroll this and think of them as 9 words. 1 2. So this will now act as these vectors h1 h2 to so on, whatever you have, right? So h1 h2 h3, the hidden state vectors, h9, and I can use this to get my uh, these attention vectors. Apply attention over this to combine all of this in the same way which we discussed there. uh, get some alpha vectors which are the weights, alpha 1, alpha 2, and so on, alpha 9. So it will be some combination of alpha I, hi, which will be my the attention condition vector. So here we are trying to mimic whatever was done in that machine translation task, but for uh, if you have to incorporate attention in visual inputs. Is this, like, is this analogy clear? Okay. So to get these scores here, right, which is the similarity of the um, previous hidden state and the input hidden states, like, so this is from my decoder and this is from my encoder, right? So ST is previous output state from decoder, HI is input hidden states. So to compute the scores, like different kind of metrics can be used, but these are all more, I think, like cosine similarity function, or use another layer of weights to compute the scores. So pass this. Yeah. Yeah. So different ways of computing the same attention scores. This is more an empirical analysis, I think. Based on what works, people just use it, but the logic remains the same. So somehow you need to compute those alphas and convert them into weights through a softmax function, so that they sum up to 1. So yeah, it's pretty much just what we discussed. If I have an image for image captioning, I'll use the convolutional layers to get my final output. And so using this, so earlier, as in without the attention mechanism, this part wouldn't have been there. So I would give a okay, not no, no, this part would be there, yeah, because this is the summary vector, this part, and the start token, and I will start decoding. But now along with this, I have another element as well, which goes from yeah, from here, like from that image features, I will compute. Okay, where is it? To that here. Yeah, from the image features, um, I'll get those image tokens. Then compute the vectors C1, C2, and so on, and then give them also as conditions here, which is this part. So after after all these works, then there was this one paper called "Attention is All You Need," um, which kind of revolutionized the whole field of natural language processing. And then they even came up these vision transformers, which was used in like uh, which is like one big shift from moving on from CNNs to transformers, even to process vision data. So like I'll discuss that. The attention is all you need. The attention mechanism more in detail. So the so this is how a transformer architecture looks like a deep transformer architecture, which is based on the attention mechanism, which we kind of the idea of which we just discussed, where if I give like input text in German, I pass it through uh, a deep network of encoder modules, and then the encoded hidden representation is then used to condition each of my decoder to get my final output. It's a much deeper version of what we just discussed. And so in this case, I keep embedding. So the first step is encoding this input into a token embedding space, like convert. So I map it. So I usually have a vocabulary for the particular language, right? So based on that vocabulary, we would have learned something called as tokenizers. Oh, I don't know. Do they discuss tokenizers in this? Yeah. So input text is first token passed through a tokenizer, which will which is basically a vocabulary of that language. Vocabulary uh, where the word, so we have a word to vector embedding. And basically, so every word is then represented by a word embedding, which could be of say 512 dimension or 1024 dimension, something based on what the tokenizer is. So these are my word representations, and then I pass these word representations through the encoder, which simultaneously takes in all the words as input and then keeps decoding. So this is how one encoder block actually, I mean, it's actually the same weights that are repeated again and again. It has something called a self attention module and a feed forward neural network. So a feed forward neural network just has an MLP and some ReLU layer, and I think it has I don't know if it has a residual connection, but yeah, some MLP it is. And then there's this self attention module. So we'll see what this self attention module is pretty much extensively used in images, text, everything possible right now. So and yeah, this is how an encoder looks, and this is how one decoder, I mean the decoder block looks like. So there is a self attention module even in the decoder block, which the functionality is the same as what is done in the encoder, and there is an encoder decoder attention, that is, so the embeddings that come, like whatever we saw there, right? I get the score vector, not no the state from my previous time step, and I combine it, and I also take in as input from my encoder. So that's the encoder decoder attention, and then there's a feed forward neural network. So this is one decoder, I mean the decoder block. So so what happens in self attention layer is, so there is no change in dimensionality, nothing. It's just a transform that we're taking these vectors together, and we're getting the same dimensional vectors as outputs, but then it's not independently processed, as in it's not like I have one network here, I pass this through the self attention block. No, in feed forward neural network, that is what would be happening. So say I have an MLP, I would independently pass, so the MLP is the same, and it's like I have a batch of features and I pass them. But in self attention, it's not like that. These become a function of everything, like, so the self attention block is like, so the z1 is equal to, it goes through the self attention block, it takes in as input x1, but it's also conditioned on what other vectors are, like x2 and x3. But here it's not like that. When I get my so let me call this as y1, so here, which is the feed forward neural network of z1, it's just a function of z1. It doesn't depend on what Z2 and Z3 are. But in self attention, each output, so Z2 depends on X2, X1, and X3 as well. Yeah, so if this is in this example, we're seeing them as four-dimensional vector, right? So the dimension of each embedding, the features keep changing obviously as it is encoded through the encoder, but the dimension remains exactly the same. So what is the need for this? Why do we have this attention mechanism? Like, any guess of why can't it be this kind of process where I independently process each of them and I get something out? So here there is no sequential process. That is the primary difference between what the RNNs and this, right? So in RNNs, um, so I have the first word, like first word, and then I get H1. Then this is the second word. I pass this, take this as input. Then I get H2. Then I take the third word. Then I get H3. But here that is not what we're. So at the end, so this is my summary vector. Summary vector of my input. But here what we are doing is we have these three vectors, we pass it through self attention, we get three more vectors. So these are not going, I mean, the feature vectors are not connected in this order at all in attention mechanisms. Okay, so what is the need of like attention? So by the word attention, it's like we are trying to induce focus into while learning the feature vectors, right? Like, so suppose if you look at this statement, the animal didn't cross the street because it was too tired. When we read this line, we know what this refers to, right? Like, we know it here refers to animal. But then, how would the model understands that it should focus on animal but not other things like street, right? So this attention mechanism actually uh, learns that part. So, like, what should different words focus on? So if this is my input words, right? Sequence of words. When I compute the self attention, that is, so I check. I mean, I basically, to compute my next feature vector for the, or in this case, like, let's look at the word it, right? So when I'm computing the feature for it, I'm getting a combination of all the features of all the words. That's what is happening here, right? Told you, right? Like, um, so here for each word, it is a function of all the others as well. So, and these are the weights. So the weight of this is represented by this orange color, what the model has learned, right? So alpha 1, alpha 2, blah 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 blah, and so on. So for this, it is some combination of alpha 1, um, x1 plus alpha 2, x2, alpha n, xn. So it learns to focus on the relevant word, like it should refer to animal. It would look at animal, right? So this is what the attention for this is high when I am processing this word. And by self attention, it need not always be it's not just about the nouns, right? um, Suppose there's a verb also in this statement, then I might want to like focus on the statement in different perspectives to look at the corresponding, like the associated noun, associated adjective, associated verb, and so on. So I can have different multiple self attention modules where it possibly this is all based on interpretation, so this is not forced learning. So the model has on analyzing the weight, so people have discovered that it looks at specific parts of the network, and it automatically weighs them correctly, like based on how we humans understand it. So if we have like multiple of such modules in one self attention, it attends, I mean, so the it learns to recognize the correct noun, suppose, and if there's another other parallel attention module that could learn something, some other aspect. So we could have like multiple self attention modules in the same like at the same level in the network, where each of them are learning to understand the text from different perspectives. Like it kind of uh, so if I have to give the analogy in images, it would be like so we would when we have a CNN layer, uh, each CNN layer we would have so many filters, right? Like 32 filters, and each of the filter is looking at the whole image and then you're processing. But if you analyze what those filters are, each filter would have been learning something, learning to recognize something different. Like one filter might recognize color, another filter might recognize edges, another filter might be attending to like some particular shapes like circles, rectangles, and so on. So each filter is looking at the input image from a different perspective and trying to capture some aspect of it. In a similar sense, if we have multiple self attention modules here also, it learns to understand the same text from different perspectives. And on analyzing them, people have seen that it learns complementary information. So using multiple self attention modules is useful in that sense. Uh, is this clear? Like the purpose of self attention, what this is doing here? Okay. So now let's look at what exactly happens inside. Like what is that function? That is self attention, right? So a self attention module has three parts. I mean, extracts three different vectors from each input. So if this is my input embedding, it extracts something called queries, keys, and values. So it gets queries, keys, and values. So queries is like so queries and keys can be kind of thought as like asking specific question and looking at the answer kind of thing. So if my query vector matches well with the key, then I would give a higher weight uh, to this particular input while combining this different feature step. So how are these queries, keys and values obtained? So the input, like these input embeddings are multiplied with this. So we have these weight matrices. This is query weight matrix corresponding to the query key and value. I multiply it with them and get a so this is what this is a yeah, here in this sense it makes sense. So if this is a four-dimensional vector, then based on whatever the query dimension defined, that would be that is what defines the shape of this weight matrices. So this is a 4 cross 3 matrix, and that multiplying this with this gives us this query vector, which is a three-dimensional vector. So in a similar sense, you get you extract queries, keys and values. Then once you get these queries, keys and values, then you compute the scores. So the scores are the products of queries and keys. So this is like sort of analogous to the scores which we computed in that previous attention thing which we discussed, right? So the scores are products of this query and key vectors, dot products of these. So we get this dot products of queries and keys. So once we get all these scores, then we need to normalize these scores. So for each of them, until now, these are independent steps. Like there was no interaction between x1, x2, and so on, right? These were independently extracted. It was just one linear layer. I mean, three linear layers. We got three vectors here, and we have computed what the scores are. So once these scores are computed, then there's this one normalization step, which is to divide it by the uh, number of the dimension of this vector here. So for this example, this should actually be 3. 3 is the dimension of these vectors, right? So it is that. So what we are doing is qk transpose by root t. So I have different queries, and then I compute the dot product with the keys and normalize it with this dimension. And so once I have computed all these scores, then I apply softmax over it. So here they've just used two words as an example, right? So then after applying softmax, you've got over these two scores, normalized scores, you've got 0.88 and 0.12, and both of them sum to 1. So this score determines how much this feature contributes to my output after the self attention. So this can be treated as my alpha I, and the output vector which I am getting z1 is summation alpha I xi. So here it will become 0.88 into x1 plus 0.12 into x2. So 0.88, once we get the weights, these weights are multiplied by these value vectors, and then we get this z. So z is actually represented by okay, not summation. So softmax over qk transpose by root t. This gives the weight vectors like be a vector like this, alpha 1 to alpha n, based on what the words are, and then I would have the value vectors v1 v2 to vn, and combining these two. If we represent this as some value matrix, then z would be this into the value matrix. So here z1, when I do this step, I end up combining the information from different word tokens to get z1. So this is what one self-attention block does, and they call something as so this is the query matrix, the key matrix, and the value matrix, and this gives us the weights, like we get a two-dimensional vector which is multiplied with, used as weights to combine the value vectors to get my self-attended vectors. So this is one self-attention block, right? So then they tried using multiple self-attention blocks. This is called as multi-head self-attention. Multi-head self-attention, where the exact same thing is done again and again, so that they capture different perspectives of the input. So you get multiple of these. So from attention head 0, I get a three-dimensional vector, then this is a three-dimensional vector, and so on. So if there are 7 such three-dimensional vectors, then you concatenate all of them to get 3 into 7. This is 21-dimensional vector. So this is the resultant vector, and then you pass this to the feed-forward network. But then when I started explaining this, I said that the feature dimension would remain the same from start to end. So but if I have to use this multiple attention heads, so what they do is divide. So the dimension of this is divided by so suppose my token embedding is of size 512 and I want 8 attention heads. So what they do is each attention head, the weight matrices would be of size 512 is the input vector dimension, and then they make it as so the output dimension would be made as 512 by 8, so that it gives out a 8 by 512. Yeah. So the each attention head output vector z for each attention head would be 512 by 8. Then if I have 8 such vectors, I can concatenate all of them and get a 512 dimension vector itself, so that the dimension is not changed, and I can continue passing it to the next one. So yeah, here they show these what the use of these different attention heads. So one attention head attends to the animal, it refers to the animal. Another refers to the action, like it was too tired, so tired. So it attends to this word, and yeah, similarly if you keep adding more attention heads, it will add different perspectives to understanding what these words mean, so that it can correctly decode this information by doing the right associations. So I said that here all the words are being processed parallelly, right? It is not done sequentially as done in RNNs. But if they are processed parallelly, um, does the order of words matter? Like if I, instead of giving this, I shuffle them and I give it in the opposite order, and I do the same, what would happen to my vectors? Would it be the same? Because I'm parallelly processing them, right? So I have the self attention mode. Order will be different, okay. Uh, so word 1, word 2 to word 5, and I will get Z1, Z2 to Z5. Okay. Then suppose I give the weights are the exact same, I give them in the other order, W5, W4 to W1. Then I have got some W5 dash, the Z4 dash and Z1 dash. So how are these related? Is there any relation between the Z1, Z5, Z1 and the Z1 prime? The weights of both are exactly the same module, same weights, everything. So the self attention is the same function. So I'll keep doing this, but at the end of encoder, I will combine all of this, right? I will combine all of this to get one Z vector, which is the summary vector. So here also I would do all of this and I would get one Z dash, which is the summary vector. Will this and this be same? Based on whatever we discussed, will both be the same? So I have like two questions. Okay, yeah, it will be the same. Is so is that a good thing or a bad thing? So how are these related? Relation between Zi's and Zi primes. So how are these related? They are same. Why? Zi is equal to Zi prime. This is word 1's output, right? How can this be equal to this? This is word 5's output. Okay, yeah, right. Yeah, so Zi would be equal to, yes, Zi will be equal to Zi prime. And my Z is equal to Z prime. So is this a good thing or a bad thing? Do I want to preserve my order, like in some way enforce the order or not? See, at the end, when I say this is my summary vector, so I want this summary to capture the meaning in these words, right? And these words are meaningful only in this order. In this order, it's just junk, right? It's junk. But these two are same. So what does that tell us? If this is the correct order of words and this is the meaning I want to capture, but even if I give it in wrong order, it's still capturing the same summary. So is this vector good representation of my text? Textual summary changes if order of words changes. How does it change? We just discussed it as the same, right? So these two are same, that is for sure. These two are same. But these being same, is it a good thing or bad thing? Is that what we want or not? No. Yeah, it's not what we want, because I want the summary is captured only if uh, correctly captured only if the order is preserved, right? I can't give random orders, and if it is the same way, then it's not right. So this is not a good thing. But then we discussed all of this, and this is how transformer is like. So what is the missing part if I have to uh, somehow incorporate this order information? Because self attention module treats each word independently, like there's nothing I can do about it. I mean, that is how it is. So what what should we do so that somehow we tell what the order is, because it's not sequence. In sequence, or the order is encoded because you are passing one after the other, right? So the order information is encoded in the summary vector, but in this the order information is not encoded. So we have to find some way to induce that order information when we pass the words input, right? Does that make sense? So in some way we have to encode words plus the order information so that we get what we expect. So to do that, they use something called position encoding. It's like so I have these vectors. The input, this is what I get from the tokenizer. So till here it doesn't matter. It's just word converted to token, converted to a vector form. Then oh no, not this the other, this this is from the tokenizer. So then they add something called positional encoding, which encodes the time information. Like, so you can think of it as this vector represents 0, this vector represents 1, this vector represents 2. So that when before I pass to the encoder, I have the embedding x1, but it also has the time information. So there are different ways they can like encode. Basically, these are unique vectors that can represent time. I mean, it's just a dictionary, right? Like for 0, I have one vector. For 1, I have one vector. For 2, I have one vector, and so on. So it could be like this binary form 0011. I mean, anything. It could be 0000. This could be 0001. This could be 0010. So that if I add this to my input vector, then there is a time signature also embedded here. So yeah, this is how this positional embedding vectors look, which you add to the text embeddings and get this. And then once you get this time embedded signal, then you pass it to the network so that it also knows the order of words. So there is something called sinusoidal position embedding, cosine embeddings, and so on. I'll not get into the details of that, but the logic is this: basically some vectors which is of the same dimension, of the input, but it's also like a dictionary, which if you add, because you are training the model, right? So when you are training the model, you are kind of saying that this means position 1, this means position 2, and so on. So it doesn't matter. I mean, yeah, empirically it matters, but logically that's what is happening. You can choose one some function to get these positional encoding vectors and use them so that your model learns what that means.
So then I have a question in the attention score computation. So when we are computing the score, obviously we'll get the highest score for the word itself.
Yes,
So
yes.
maybe including that will bias the model. So it should be intuitively. I think that we should not include that thing while we are summing up everything.
No, but when you are doing forward pass, when I'm going from this x to z, right? Um, so from this x, I'm coming to z. At the end, I still want that x z to represent that word itself. So it has to be that word representation, right? So this extra part attention, what we are doing is so that it can incorporate some neighboring information, but the most important information is obviously that word information, so you should include it. Suppose I remove it, uh, and I only look at the others and get this calculation. So what am I, my z is only having neighbors information, it is not having its own information at all. But for the next step, that becomes the identity of it, right? That means after my first step I have lost my identity and I am only having my neighbor's information. So each word will only have its neighbor's information, not its own information. So when you're processing with time, where is your original word's meaning? It's not there, right? So by doing this whole attention thing, what we are doing is, yeah, of course the weight will always come highest to this, but how much do others contribute is how you are trying to incorporate some the context of other words. But you don't want to lose what your original word is, right? Because that becomes the feature for my next layer. So for my next layer, if that becomes a feature, that has to be the representative of what that word means, considering the context. See, your model can still function fine if you remove the self-attention module, as in like removing the weighting part. It will become like a feature extractor, right? Feature extractor with some order, it will still work reasonably. But if you remove your word vector, it can't work. Does that make sense?
Yes.
Yeah, so along with this, yeah, that was the simple encoder block which they showed. So along with this, so there's like self-attention model, feed-forward network. Along with that, they also add these residual connections, which which helps the gradient propagate backwards, right, in a deep network. So they do that as well. Yeah, and then there's this normalization function. But yeah, so those are all the details, tiny ones, but I hope you have understood the concept. Yeah, so once you have yeah, the encoder part we discussed, yeah, and decoder part I forgot about this. So once we have done all this, at the end I will have one summary vector. So there'll be like one fully connected layer here. I don't think they've shown that here, and which basically combines all those word vectors and gives out one vector z, which is used as the what my input context, right? That summary vector which I use while decoding. So that what does the feed forward network in the encoder do? It is a step to learn. So see, self attention part is to get weights and combine your features, right? So feed forward network is your feature extractor basically in the forward pass. So the in most simplest encoder is to just have feed forward network. That is like just a sequence of fully connected layers. I keep passing them and I keep getting my features. Then we add this self attention part so that it can encode context. But this is your feature extractor primarily. So yeah, once we have this summary vector in decoder, so the decoder architecture is also very similar to the encoder, just that there is this another encoder decoder attention. So it has self attention, residual connection, feed forward network. So because whatever has come, no, I have translated like word 1, word 2 in the new language. So obviously I have to process what those words are and give it as input to the next token, right? The same logic as in RNA, like the early decoder thing what we discussed. But this step is where I'm taking in the previous word tokens output, right? Like this is the z. or in the early case wherever we saw st minus 1, right? It's like that. So this encoder decoder attention basically does attention between this and this, like the decoder inputs and the encoder's input. So the encoder decoder attention part mein what happens is the so we have the summary vector from the encoder, right, like z. So that is passed through like key and value matrices to get this keys and values. And then so the queries is what we get from the decoder, like this input. So this acts like the query, and then the encoder input acts like the key and values, and then there is this comes from the decoder. And then we compute the weights based on the alphas is, so query is from decoder, k transpose by root t, that softmax thing, and then you compute the value vectors from that encoder decoder intermediate step here. You get this, and then you combine summation this alpha encoder decoder, and then this z z decoder, whatever we have now, z decoder of I or something like that. You combine them here. So here it's like I'm taking the summary vector and the previous I mean the current decoded word, like in the new language, and combining both of that information to get my next feature, and so on. So it's slightly different from the self attention module. It's like cross attention. So yeah, after I do all this, the whole decoder, then we get some vector here, which you pass it through a linear and softmax layer to predict the output word. So what should the dimension of this linear layer be? So based on what language I am translating to, how can I decide the dimension of this linear layer? Size of the vocabulary, right? Vocabulary. And the loss is what? CE loss itself. It's like word predicted versus true word, right? In that language, CE loss over that, and all these this one dimension will be size of vocabulary. Can you see my screen? I had seen this sometime. Just one.
Yes.
So here the kind of demo what happens in this transformer thing. So here this is like sentence completion task. Looks like, yeah. So the first line starts from what they start from data visualization empowers user to, and then the task is to predict the next word, right? So they've taken this one transformer block and the first head in the first transformer block, and so this, so like you extract in what happens in self attention, and one of the block we compute this query key value vectors for each of these words. There are 6 words here, and then key query values are computed, right? And then these are the similarity values that are computed, like 1, and then how much that word This is the decoder attention actually. This is the encoder decoder attention part. This is one important thing which I missed saying actually. For the so when I see this matrix here, this is all query key similarity matrices only here, right? Like query key, multiply them, like get the similarity values. That's all this is. But what in self attention, it should some so here this first row I see this like this number is 1, and here these are all null, like there's nothing existing here, these are like zeros here. Okay, why is that? Because it's like this is my first word and this is my only input I have, and I have to use that to predict my next word. So like my encoder, I don't until I mean my encoder has so until now I would have only seen one word, that is data, and predict what the next word means, which it would have predicted as visualization suppose. And then here to predict the next word at this stage, once I have two words, that is data and visualization, there are two vectors here, two numbers, 0.84 and 0.16. So this is how much data is attending to the same the word data, and this is how much data is attending to the word visualization, and it's 0.84 and 0.16. So using these two, it would predict the next word. And so in decoder encoder decoder self attention, you can only see the tokens that are predicted earlier, right? So for my next step, the number of tokens I have in my decoder will keep increasing. Like at the first step I have one word, in the second step after I've done that, then I have two words. So that is why this matrix looks like this. So at this stage, users 2, here there are 6 words here, and this shows how much 2 attends to the word data, how much 2 attends to, you can see the one that are highlighting, right? So this is 2 attending to the word data, 0.25 is the score. 2 attending to the word visualization, 2 attending to the word powers, users, and 2 its own. And then based on this it combines all of them. Oh yeah, so earlier when I said that the highest weight will mostly be to its own, but for these kind of words, when it is meaningful like nouns and all, mostly the weight will be more to its own. But for the words like to, the, and all, it will still focus on the important words, because just based on to what would I predict, my focus should be based on the context earlier, right? So that is why it attends to like even other words with like reasonable weights. So it's spread out attention here, right? But for these kind of words it's more concentrated. So here based on all these predictions, so I combine these query keys and then with values, and first time it would have predicted visualization. So using 2, it then here, so this is the what encoder decoder attention, then there's an MLP, then there's some dropout layer which is used, layer normalization, then there's this residual connection, this, and so this is transformer block 1. So there are so many more such blocks, like 11 more. So in total this model has like 12 blocks. So same thing is done again and again, and at the end for this what it predicts is the word easily. So here it shows for just using 2 words. I'll share this thing here, you guys can play around. Oh, okay, artificial intelligence is transforming the way. So this was one attention head, right? So if I see some other, okay, this is another attention head where it has not learned to do anything, it is just given 1 1 1 1 for all of them. So it's like identity it is passing. And then here It is, yeah, it's some other. And so this weight should be different. So some different perspectives should be learned in each cases, I think. Yeah, here it's like almost one, but like slightly it is attending to something different. It's not always that the attention heads you could like have direct mapping, but usually in some way it will understand things in a different perspective. So this is that first step, like where before I pass it to the encoder layer, what's happening. So the word, these are my words, right? Then I get the ID from token embedding. So I have a tokenizer, which is like the vocabulary, right? Like I have the word, its ID, its vector. So I get its ID, get its vector, and then I add positional embedding, which is 0, 1, 2, 3. These are the positional embedding vectors. That's like those cosine embeddings are there, right? Those. So this is that time signature which I'm adding, and I get these time encoded text embeddings. Yeah, so these how this tokenization happens depends on how the model like that tokenizer is trained. So apparently GPT-2's vocabulary is 50,000 to 56 tokens. So if whenever we are doing this sentence completion, right, if whenever we are using GPT, it's actually predicting picking one word over such a huge vocabulary. So this part is the self-attention part, I think. Okay, whatever, anyway. Yeah. So for each word, we'll get this query key value matrices. Basically extracting the queries, keys and values. So the queries are the blue ones, keys are the red ones, and values are these. So we have three vectors for each word. So once you get yeah, we get, so this is what dimension. This is 2304 is the that what token embedding dimension 2304. Then multi-head splitting is where we define divide them based on the number of heads. So if they decide 12 heads, then they divide this by 12, and so that would be those query key values for I mean for each of them, and then you combine them. So the, yeah, this is the decoder part. May what they do is this masked self attention. That is, so see, if we simply compute query key product, we can compute it for all of them, right? But to predict for next words predictions, I only want to see what the previous words are, and based on that predict it. So this is something which we have to force and do while training, because while training we obviously have the whole output, right? But we should not use the whole output at once. It should be used in a sequential manner, right? It should predict the first one, then the second one, and so on. So that is why this mass self attention is used, where these values, yeah, these values are forced to, I think, minus infinity, so that it will map to zeros in when we put softmax function, right? So softmax, if the input for softmax is minus infinity, then it is zero. It gives out zero. So for all these values, like if the index 1, then for all the other ones it will add whatever this dot product is computed. So this they just compute directly, because it's like matrix operation, right? Multiplication, they just do it, and then like, which is computationally easy than doing it on individual elements. So they just do this, then add like minus infinity to this upper triangle, so that it gets blocked out, and then here you get these normalized weights where each of these rows sum to 1. Here it will be 1, here these two will sum to 1 here. So scaling and mask, and then you apply softmax and dropout to get this. So these will be your those weights, attention weights, which you combine with these values to get this get the output features for each of those 5 words. Then the 12 attention heads are combined. That is a simple thing. which you then pass through an MLP and blah blah blah. And finally, you have this logit vector. Um, so in this once you get this logit vector, then there's this temperature parameter which is like multiplying. So I multiply this logit with this vector, or not this vector, divided by, so logit divided by this temperature, so that will give me scaled logit. It's like minus 135 by point. It kind of controls the skewness of the probability distribution. So here uh, we have everything in this range of minus 135 to 138, right? So it's like okay, that's another whole topic of discussion, so I'll not go there, but it kind of controls the skewness of the probability distribution between 0 to 1. So these are the scaled logits, and then based on this I give out my predictions. So for the first word data, I think it would predict visualize, something like that. So these are the top ranked ones for the using the word data. Yeah, so if I use lower temperature, it makes a model more confident. If I use higher temperature, then it will make it more spread out. Yeah, so these are all heuristics, but yeah, this is a very nice demo. So this page has like the code and its detailed explanations. Maybe yeah, for the next 10 minutes I'll quickly go over that. So this is like the base class for the any encoder decoder model, right? Questions related to this week? You can see this, right? I forgot about this actually. Okay, with regards to the context vector based attention mechanism, which of these statements are true? Can the alignments weights be positive? The alphas which I used to combine. In we discussed so much like in all attentions the weights, right? So can they be negative?
No.
Huh? No, right?
It's-
So the first one is false, right? It has all of them have to be. So the similarity values when I compute can be could be negative because of a cosine similarity, but then at the end when I mm, pass them through softmax something, I need to combine them. I mean, get a positive set of values that combine to one, right? So the first one is false. What about the second one? So in that context vector, if I only take the first, so if I am at say I'm at some second third word, I'm computing C3, then if I use only the hidden states H1 and H2 versus using say it's a 5 letter, I mean there are 5 words for third one, instead of using all 5, if I use only the first two to compute first two like the first three to compute C3, so would that be better or worse than using all of them? What was the point of using attention and combining everything, past, future, everything? It it may not work well, right? So, um, irrespective of that information that comes in the later words is useful or not, if I anyway let it pick the weights automatically, it could assign really low weights for those last two words. There is so much flexibility, right? But if I'm limiting it, then I'm only looking at the past. So, but in those words, so there was that what I think, what was it? Something, the forgot. Yeah, that aspect, the activity, right? That someone is tired. So that was a word in the future. But using that would help me understand the whole statement, right? Right. So if I don't use that, then I'm not I mean capturing that information. So it may not work as well if I'm limiting what I'm seeing when I'm computing that context vector. It may still work as well as without those connections since future inputs would depend on previous inputs. But then in the third statement, so that would reduce to it being an RNN, right? In which at current step I'm only seeing what is there till first. It just becomes like I'm adding one more CT, but in terms of the access to information, I'm not really changing anything. So it's like some modified version of some RNN. Such a mechanism can be made to work for spatio temporal data such as videos. So can we extend this attention logic to have both image and like text?
Yes.
Yeah, right. It's just so instead of having five tokens, I have five tokens from one more image token as well, suppose something like that, or a sequence of image tokens, and I'd put this attention. So this is because of this kind of mechanism, it becomes really simple to extend it across modalities. That's why like all these gpts can now combine multiple modalities like image, text, audio, video, everything, because at the end everything boils down to their fundamental elements. So it's either words like word embeddings or images, like say image patches embedded, so they are like visual words. So at the end they all become those fundamental elements and they just become features, multimodal features, which I combine using the self attention so that it looks at everything, processes everything, and gives out what it wants. Okay, so which of these are false? Is the first statement true or false? Is this so hard a question? The first statement, is it true or false? After seeing everything you saw.
False.
Huh?
It is false.
Why is it false? They're saying
Because
it.
in both the cases, the caption is generated word by word. So that is not the reason.
Huh, both the cases the task is done, but doesn't this attention have more explainability aspect, because you can see which words are contributing where, why it is failing means I can see why it is something is failing, I can understand better, right? But in RNN I only have one vector which is a combination of my whole history. So which, like which aspect of my previous part is actually contributing for my next word to prediction to fail, it's very hard to understand that, right? But if using this attention mechanism, I could see which region in the image or which region in the previous words predicted, based on that attention. If it is attending at a wrong region, so it might be predicting wrong, right? So I can at least understand where, why it is giving what it's giving. It is more explainable, right, than RNNs. Any cases, failure cases where it works, everything becomes more explainable because you can visualize and see what this attention models or I mean mechanism is doing.
Yes,
The decoder of a visual dialogue system cannot be truly discriminative as it involves computing the maximum likelihood of the correct option. So here also visual dialogue is also like asking questions and about an image and getting answers to them, right? One after the other. So when I am trying to get an answer from it, I am still doing a discriminative task, that is from the vocabulary or the given choices. I'm trying to pick one. So it is a discriminative task, right? So the second one is false. Blue scores are between 1 and E. They're between 0 and 1, right? Transformers are parallelizable architectures. Are these parallelizable? Any models can be run parallelly on multiple devices and does not feature of just transformers or RNNs. So that's also false. So which of these are true here? Do vision transformers do not require positional encoding as they are not temporal data. Like I'll just say what vision transformers are. Where instead of so in statement we give sequence of words, right, one after the other. In vision transformers, what they do is they create from the image, they make them into different patches. Like that time in one case I discussed, right, like 9 patches from the image and pass them as 9 different patches. So do they require positional encoding or not? Can I give those 9 patches in any order, and is that fine for a transformer? So does it
They
require
require positional encoding.
Hmm?
They require positional encoding.
They do require, right? Because I should still know this is my topmost corner, this is my bottommost corner, this is the center of the image. I still need to understand that, right? Otherwise, the image is meaningless if the order is not given. So even vision transformers do require positional encoding. So input data is parallelly passed to all the stacked encoders in a transformer. So I have several encoders, right? One after the other. So can I directly pass it to all of them in parallel, or should I wait them, like pass it to the first encoder, get the output, then the second encoder? So it is a sequential process there, right? After first I would pass it to the second and so on. So the second statement is false. Input data is parallelly passed to all the stacked decoders from the last stacked encoder. This is true, right? Like if you remember that image, so I have the summary vector, that same vector goes to each of the decoder, so I can parallelly pass it to all decoders. The weight values in each of the QKV matrices of multiple heads of the first encoder are kept exactly same, but the inputs to these matrices are kept varied to ensure better generalization. So this can't be right? When so if I give the same input to 3 different matrices QKV, I want to get 3 different vectors, right? So that they mean as query keys and values. If I initialize all three those weight matrices to be the same, then I'll get out the exact same thing. So they're not, the query key values don't mean anything different in that case. So the weights should be different for each of those matrices. So that is pretty much, I think, what I have for today. Oh God. Okay then. Thank you. Thank you. See you next week.